Okay, so in this video we're going to start talking about how we predict pollution movement in rivers. And as we've already talked about, there are two main processes in moving pollution anywhere, and rivers are no different. There's advection, movement with flow, in this case that's just downstream, and then spread due to Fickian mixing, dispersion and diffusion, whether the diffusion is molecular or turbulent. So in this video we're just going to talk about advection, movement with flow downstream. And I'm sure you all know water flows downhill. Really this is down potential. Don't worry too much about that yet. I just wanted to introduce you to the term. It'll come up again in groundwater. So movement or velocity is created by downhill flow, and velocity we're used to thinking about in terms of length per time. So that's nothing new. In a river, however, velocity is not uniform. That may be something new to you, probably not though. Here is a side view of a river. So this is the water surface, and here is the riverbed. So the fastest part of the river is right below the surface, where there's no drag due to either the surface tension or the surface of the water or the riverbed. This is a bird's eye view. So this is a riverbank, this is a riverbank here, and the fastest water is right in the middle because there's no drag along the banks. This is just another sort of picture of non-uniform velocity in a river, with pink and white being fastest in terms of meters per second and blue being slowest. So you can see not uniform. So in general we just use average velocity to do all of the calculations that we'll do in this class. So whether that's average velocity across a width or within a reach or length of river, so a reach or length that you're interested in, whatever distance that is. It could be just here, or it could be this entire length, or more than that. And in general, to get average velocity, you take several measurements along the area that you're interested in with flow meters, or if you're really low tech, floating objects and a stopwatch work fine too. And just average all of those measurements to get your average velocity. Okay, so velocity, again, you're used to thinking about it. It's just length per time. So in symbols, that's just v for velocity by equals length divided by time. And this t looks a little bit funny. I'm keeping the same notation as in the book there, and the t looks a little bit funny because they use it to stand for travel time, which you'll see here in just a minute. So velocity can help us estimate either the distance traveled. So if we know velocity and the amount of time that something's been in the river, we can estimate how far it's gone. And we can also estimate how long is it going to take for a chemical to move downstream. So this would be the distance that we're interested in, and this would be the velocity that we know, and we can use those two things to figure out how long is it going to take to move that distance. Okay, with velocity and pollutant concentration, we can go ahead and estimate flux density. So this should look very familiar to you, this J for flux density, or advective flux, being equal to the concentration of a pollutant times velocity. And this tells us, again, how much chemical is passing through a given area, like a cross-sectional area of a river, per unit time, with concentration and mass per volume, velocity, length per time, and flux density, again, with these sort of funny units that just mean how much, what mass of a chemical is moving through a cross-sectional area, in this case of a river, over a given time, per second, per minute, per hour, per day. Okay, but we might rather know how much of a chemical is being transported past a given point per time. So if you're just standing on the side of the river, how much is going by you in terms of mass? So for this, we need to know discharge in units of volume per time. And this is something that you've already dealt with in lab. I believe you've already had to use this formula. So discharge, we use Q, is equal to the cross-sectional area of a stream times the velocity, average velocity of that stream. So you end up with a mass of water, or a volume of water, excuse me, per unit time, something like meters cubed per second. Okay, so then you can use discharge to calculate the mass of a chemical transported by a river past a given point per unit time. So this is just mass of chemical per unit time in a river. And we call this J total, or tote. So that's discharge times concentration. And you've actually by the time you're watching this, you'll have already done this sort of in the mass balance calculation. So this is sort of like the output at times the concentration of the lake. So it's the same idea, just in a river now. Okay, so that is our main equation for dealing with advection. And the next video is going to start talking about spread in a river due to dispersion and diffusion.